Hi everybody. Today in our video we're going over vectors part 3. We're again just going to have 3 practice problems for us to go through to get more familiar with how we're going to be using vectors in this course. So we'll kick right off. We've got 3 vectors. Add the following vectors by the component method. Give the resultant vectors magnitude and direction and show all work below. So as with ASCII's class, we often require you to sketch out the problem just so that we know that you understand what's going on, right? So before we do stack and rack, which is a method I'll go over in a minute, let's sketch these vectors. So I want a 45-degree angle for the first one. That's 56 newtons at 45 degrees. I don't know how I'm going to do 56 newtons. Oh, it actually gives me a number. Well, so this might be a small drawing. Okay, that's about 56. And no, that's too small. Let's just draw it approximate. Okay. So that is about 56 newtons, what we're going to call 56 newtons, 45 degrees south of east. So I drew my 45-degree angle south of the east line. The next vector is 14 newtons, 22 degrees north of west. But we need 22 degrees from our vector right there. So this is 14 newtons. Let's see, that's significantly smaller. So we will end our vector right there. Put a little arrowhead on it. And then we will draw 84 newtons. So this will be much bigger of a vector, 10 degrees south of west. So we need 10 degrees south of west. Let's get that 10. And let's move that up over there. This needs to be much longer than the other ones, right? And as I draw the arrowheads, I am strategizing to think, where is the next arrow going to go? Right. Now, that looked to be 32 degrees. Let's see if that's actually what we're going to get when we do our math. Because remember, I'm not measuring the lengths, so if the lengths aren't right, your drawing isn't going to be as accurate, right? So instead of going over drawings, remember we want to go over math. We want to move away from relying on drawing our methods, and we're going to try and move towards pure math. So stack and rack can allow us to do this. What we're going to do is we're going to combine these vectors by the component method, right? Component method, meaning we're going to get an I and j component of these vectors, and we're going to combine those. So first we have 56 newtons, that is 45 degrees south of east. These are polar vectors, not Cartesian vectors. So we know the hypotenuse is 56 newtons, and we know the angle is 45 degrees. So to get the I component, here, let me do this. So if we want the I component and the j component of this angle, theta, right? But we know the hypotenuse. So this is how you get the I and j component of a vector. To get the I component, right, you would use cosine, right? SOHCAHTOA, cosine is adjacent and hypotenuse, right? Okay, we're back. So to get the I component of a vector, you will use cosine, right? The I vector would be, now here, let's do that differently. You would take the magnitude of your vector Well, since it's f1, then you would multiply that by cosine theta. Then to get the j component, you would take the magnitude of your vector, f1, right, up here, and then times sine theta. And all we're doing is we're solving for that leg of the triangle, right? Because it's a right triangle. We can do this. And if we want to work through the trig, I can definitely do that real quick. Here, let's scroll down here. So let's say we have a right triangle here, angle theta, and then we have our vector right there. If we want to find the x or y component, if you look at cosine of theta, that is adjacent over hypotenuse, which is x over r. If we want to solve for x, multiply that r over, you get r cosine theta would give you x. Similarly, if you have sine theta, that would be opposite over a hypotenuse. So if you want to solve for y, multiply that r over, you get your y component. Right? So that's the math that we're working with here. Another common thing we're going to do is we will use tangent theta equals opposite over adjacent, right? So you have y over x. We won't use that often to find the length of something. We'll use that to find the angle, because oftentimes when you have a vector, you have the x and y component, so you can find the angle easily. So if you want the angle of a vector relative to the x and y axis, you would take the tangent inverse of y, let me keep my y's consistent, y over x, right? Now, when we work with vectors, we're converting all of those x's to i's and those y's to j's. But that's the math that we're working with. So let's go back up here. We've got our i's and our j's. So let's stack and rack. This is a method that we're going to use to add vectors. So we're adding these three vectors using the component method. Component method is when you just combine all the i's, all the j's, do all that math. So we have first, we have 56 cosine of 45 degrees. And that is east, right? East is positive in the I direction. But it's south, so that's negative in the j direction. Then we have minus 56 sine 45j. Then for vector 2, we're going to rinse and repeat, use the exact same method. We're going to look at our direction. We have north and west. North will be positive j, west is negative I. So we have negative 14 cosine 22i plus 14 sine 22j. Then for our third vector, we have south and west, both negative. So we have negative 84 cosine of 10 I hat. And then we have minus 84 sine of 10 j hat. Now, if we want to put that all in your calculator real quick, I'm rounding just to an integer. I'm not using any decimal points. So 56 cosine 45, that is 40. 14 cosine 22 is about 13. And then 84 cosine 10 is about 83. That's in the I direction. Then we have 56 sine 45. That is again 40, but this time it's negative. Then we have plus 14 sine 22, which is about 5. Then we have minus 84 sine 10, which is about 15 on j. So that means that our vector has the coordinates, if you do all that math, that comes to negative 56 I hat minus 50 j hat. So if you look over here, that means this would be negative 56. This would be negative 50. If only I had drawn that to scale, right? It's obviously not negative 56 and negative 50. But so that's the component method to get that vector. Sorry for the sloppy penmanship. But what they want is they want this back into polar coordinates, right? If you see, sketch the resultant vector above in a different color and give the proper description for the resultant vector. So what we want now is we want the length of the vector. We need the magnitude. So what can we do? We can use the Pythagorean theorem. So r will equal the square root of 56 squared plus 50 squared, which comes out to about 75. So that would go right there, 75 newtons. And now we need the angle. Like I told you before, the angle would be tangent inverse of opposite over adjacent. So if we want that angle there, opposite is negative 50, adjacent, negative 56. So that will come out to 42 degrees, and that is south of west. And you can tell that just by the coordinate system, right? Looking at that red vector. So that's how you can do the component method if you have three vectors that you need to combine, and they are all in polar coordinates. So you have to convert that to Cartesian in I and j hats using unit vectors, and then solve from there using Pythagorean theorem and the tangent inverse rule to get the angle. All right, next problem. You are standing on the ground at the origin of a coordinate system. An airplane flies over you with constant velocity parallel to the x-axis and at a fixed height of 7.6 times 10 to the third meters. At time equals 0, the airplane is directly above you, so that the vector leading from you to it is r naught equals 7.6 times 10 to the third meters j. So since the vector only has j, that means it is just one vertical vector. It has no I to put it at an angle, has no z to do anything else to it. J is vertical, so it's just straight above. At t equals 30 seconds, the position vector leading from you to the airplane is now r30 equals 8.04 times 10 to the third meters I plus 7.6 times 10 to the third meters j. Determine the magnitude and orientation of the airplane's position vector at t equals 45 seconds. So let's work this one out. First, let's draw it real quick. So this is our r naught. Oops, that was not great. Let's try that again. So that, I should have put that on the other side, plan ahead. Okay, so our vector for r30 will look like that. Then for r45, same height. Let's get that straight line. Sorry, I got booted from the meeting again. So straight up, same height, plane is at a constant altitude, but then it has traveled much further at a constant velocity, remember, constant velocity parallel to the x-axis. So now this vector will look like so at r45. Okay, so we want to know the magnitude and orientation of that position vector. So you can guess that the j component is going to be 7.6 times 10 to the third meters j hat. we know that for a certainty, right? It's at a constant altitude. We just need to figure out what is the x component. What is that I? Real quick shortcut that you can do for this, right? Say, for example, you wanted to know the x component at 1 minute, right? Because we know what it is at 30 seconds. So what would it be at 1 minute? Well, at constant velocity, right, you would take that R30I component, multiply it by 2 to get the R60I component, right? Well, if we just want the component at 45, what we'll do is we will change that up. We will then multiply by 1.5 to get the R45, right? Really simple way to just algebraically get to your answer quicker. So we will take 8.04 times 10 to the third, multiply that by 1.5. And I already did that math somewhere. Oh, there it is. 12.06 times 10 to the third meters. So that is now our I component for R45. So we've got, here, let me rewrite that real quick. So we've got R45 equals 12.06 times 10 to the third meters I hat plus 7.6 times 10 to the third meters J hat. That little menu there won't let me write on that side. That's not allowed to write there. So that is our vector, but it wants the magnitude and orientation, basically asking for polar coordinates, right? So how do we get the magnitude? Well, we're again going to do Pythagorean theorem. So we can drop this down real quick. Let's see, if we want R45 magnitude, what we'll do is we will take the square root of 12.06 times 10 to the third quantity squared plus 7.6 times 10 to the third quantity squared. Okay. Just Pythagorean theorem that. You will get 1.43 times 10 to the fourth. Or 14.3 times 10 to the third, however you want to put that. That's really up to you. Then it also wants orientation. So again, if we want orientation, use theta equals tangent inverse of the j over the I, right? So that would be tangent inverse of the j, which is 7.6 times 10 to the third. You divide that by 12.06 times 10 to the third. And that angle will come out to about 32.2 degrees. Now, to give an answer, our vector, R45, equals 1.43 times 10 to the fourth meters at 32.2 degrees. But our coordinates are really just, let's see, what do we have? We have x-axis is just in any given direction, and y-axis is just altitude. So we don't have north, south, east, and west. A couple ways you can say that is you can say that's 32.2 degrees above the horizon, or you can say that is above the ground. Either way is going to be correct. Above horizon is more often used if you say above ground. That's not too big of an issue. Okay. All right, this last one is a bit of a doozy. Okay, so an air traffic controller observes two aircraft on his radar screen. The first is at an altitude 800 meters. horizontal distance 19.2 kilometers and 25 degrees south of west. The second aircraft is at altitude 1,100 meters, horizontal distance 17.6 kilometers and 20 degrees south of west. What is the distance between the two aircraft? And then we gave you the hint of what to do with your axes. So these aircraft are very close together angle-wise. So if we were to actually graph this, here, let me use this to get it. Just go straight 90. Get rid of that. So the first one will be 25 degrees south of west, 25 degrees. Some arbitrary drawing that I'm going to make of 19.2. And then the other is 20 degrees. So you see that these are very close together. Whoops. Let's move that a little bit. Okay, and it is a little bit shorter of a vector. But both are very close together. Here is plane 1. There is plane 2. So pretty short distance that we're calculating, right? So what we're going to do here is we are going to first write out these vectors in component form, because we have all the information we need. Our x-axis is going to be west, so keep in mind what that usually means is that west is negative, but this time x is going to be positive to go west. Y-axis is going to be south, so again, that is usually negative to go south, but it's positive this time. And our z-axis is vertical. We're not going to draw that. I can't draw 3D graphs very well. So let's do plane number 1 first. Okay. Our I component, we have our vector at 19.2 kilometers, 25 degrees south of west. So we will take 19.2 cosine of 25 degrees, and that is west in the I direction, so that is positive. And then it is also south, so that will be positive 19.2 sine of 25 degrees j hat. Then for the k hat, now we have a third unit vector. So that's vertical. So we have an altitude of 800 meters. Everything so far is in kilometers, so let's keep that in kilometers. That would be 0.8 k hat. Okay. And there should be a bracket all the way around that to say that's kilometers. But again, I'm butting up against that here. You know what, let me try something else. I zoom in, whoops, zoom in, then I can write kilometers. I would do that a little carefully. Bingo, bingo, bango. All right, so kilometers is now over there. All right, sorry, I got booted again. Now our next vector, we have a magnitude of 17.6. Multiply that by cosine 20 degrees I hat. Again, everything is south of west, which are positive directions, so we'll keep everything positive. 17.6 sine of 20 degrees j hat. And then our altitude here is 1,100 meters, so 1.1 j hat. Oops, that should be a bracket, all in kilometers. Okay. Now what we'll do here, we want to find the distance between the two. So if we added these two, we would actually be doing the head to tail method, which we don't want to do, right? We want to find the difference between these two. So what we'll do here is we will subtract these two vectors from each other, okay? So if we take 19.2 cosine 25, you get about 17.4. Then you have 17.6 cosine 20. It's about 16.5 I hat. Next, you have about 8.11 if you do that trig. Then you subtract 6.02. That is j hat. Then 0.8 minus 1.1, that is negative 0.3 k hat. So our vector, the resultant, you would get as 0.9 I hat plus 2.09 j hat minus 0.3 k hat kilometers. Okay. So that is our vector. That is not what it asked, right? It asked, what is the distance between the two aircraft? It also doesn't want to know the orientation. It just wants to know the distance, which means all we need is the Pythagorean theorem. But we have three components. Well, luckily enough, the Pythagorean theorem works in 3 dimensions. So what we'll do if, whoops, we don't want that, we want magnitude. That would take our I component plus our j component plus our k component squared. And then you plug all that in. So let's do that. We have the square root of 0.9 squared plus 2.09 squared plus 0.3 squared. That negative gets squared away. And you have a distance of 2.3 kilometers, which is kind of close in airplane land. They are a little too close for comfort on that one. There are only 300 meters difference in altitude, as you can see in that K component. So that's getting really close in altitude. They're only 2.3 kilometers away. They are. That's probably why the air traffic controller is paying so much attention to them. Right? Okay, those were our 3 practice problems for this video. We have one more, vector part 4, where I will do 3 more practice problems to sum up our vector chapter. Then we will go on to some 2D kinematic.